everybody for coming, and I hope that my sound is good enough for everyone to hear. Somebody should holler if there's any technical problems. But at this point, after a semester of teaching, I think I've gotten pretty decent at broadcasting from my tablet here. So thank you so much for inviting me to ZORP. It's always a pleasure to be sort of talking in Paris. I just found out that there's going to be breakdancing in the Olympics in 2024. So please invite me to talk for Paris and Rio in the summer of 2024 because I'm extremely excited to see Olympic breakdancing. Let's put that in our calendars. Okay, so yes, ZORP. I'm going to report on kind of stuff around questions about rational points on stacks, which those of you who I had the pleasure to be with at the trimester last semester in Paris heard me talk about a lot. And so in some sense, my goal here is going to maybe be to say some things that I usually run out of time and don't say when I talk about this body of work. And so I'm going to start with just like a bunch of questions and then try to sort of unify them about halfway through and explain why they're all species of the same question. So let's just start. By the way, I was very organized when I started writing these notes. So we see section 1. There are no more sections. Sorry, then I just eventually just started writing stuff down and stopped breaking it up into sections. So I guess this whole talk will be section 1. So here's a question: how many isomorphism classes of elliptic curves over Q are there? And I'm going to write everything over Q for this talk, sort of for simplicity, but just about everything I say is going to be a good question over an arbitrary global field, and it is sometimes with some characteristics excluded, and it's fun to think about what happens in those cases. Okay, but here's the question, such that E has a rational 5 isogeny. Okay, so we know that's x not a 5 is a rational curve, so like a lot. So we're going to put some bound, and the usual thing we do when we count elliptic curves is we count by the so-called naive height. So if my elliptic curve has a Weierstrass form of x cubed plus ax plus b, where we sort of get rid of any spurious primes that appear that can be divided out. So we put it in minimal Weierstrass form, as we say. And then we just require that the maximum of a cubed and b squared be less than x. And that's a very typical way to cut ourselves down to some finite population of elliptic curves. And there's an answer to this question. It was worked out by Brandon Bogus and Soumya Sankar, 2 students of mine in the archive this year, that the number of such curves is bounded above and below by a constant multiple of x to the 1/6 times log squared x. Actually, we don't know the constant here, and that's going to be a theme. Almost nothing I talk about in this talk today. Oh, thank you, Ronald. I did see the chat. Actually, a problem in my teaching too, so it's I know how to fix it. So yeah, so we don't know the exact asymptotic formula. We don't know the constant here, but we know the order of growth. It's x to the 1/6 log squared x. And let me comment that this follows on a little bit older work by Rob Heron and Andrew Snowden from 2017, where if instead of asking for a 5 isogeny, I ask about elliptic curves with a 5 torsion point, you get something on order a little bit less, x to the 1/6. And I should say that there's nothing special about 5 here. I just put the 5 in because I think it's sort of charming that there's like a square of log. That's the only case we know where that occurs. So in Brandon and Soumya's paper, they count elliptic curves with n isogenies for a whole bunch of n, kind of the usual suspects, the n's you would expect to see. And similarly, in Rob and Andrew's paper, they also count. In fact, they do every possible there. We have this sort of finite list of torsion possibilities over Q that we know from my advisor Barry Mazur, and they count them all. And in that case, by the way, it's always, well, I think it's always a power of x and there's never a log. Okay, but I'll just comment that notably absent from this list is 7, and we actually don't know how to count elliptic curves of bounded naive height with a 7 isogeny. And I'll try to circle back and explain like what makes that problem. Why is 7 more difficult than 5 and 8 and 9? I'll say something about that in a bit. Okay. Okay, so that's one question. Here's another. This one requires a little bit of notation. I don't know if people will think this notation is gross, but let's say if I have an integer a, by a to the ceiling 1 over m, what does that mean? It means I'm trying to I'm trying to take a to the 1 over m, but that might not be an integer because a might not be an mth power, right? So at various primes, the exponent of the prime appearing in the factorization of a might not be a multiple of m. So I just say each prime appear the power to which it appears is I try to take a to the 1 over m, and then I round up using the ceiling function, and this gives me some integer. So for instance, if a actually is an mth power, then this quantity really is a to the 1 over m. Whereas if a is square free, so every prime appears just one, the ceiling of 1 over m goes all the way up to 1, and so you just get a. I don't know how that got moved down. Look at how skilled I am. I can just do this now. Okay. Everything I've learned this this semester. Okay, and then let's make the notation even worse. And say a to the ceiling 1 over m minus 1 over m is just, you take this a to the ceiling 1 over m, and then you divide out by the actual a to the 1 over m. So now you have something that's not necessarily an integer. It's a real number. I actually originally put this as like an exponentiated fractional part, and then I decided that notation was like too terrible to use, so I'm leaving it like this. Okay, so for example, this is easiest to sort of say what it is in the case m equals 2. So that a to the ceiling 1/2 minus 1/2, one way to think of that is like if for every prime that appears to an even power, you get nothing, right? Because this ceiling, you have the ceiling of ORD PA over 2, and that's equal to ORD PA over 2. So there's no difference between ceiling 1/2 and 1/2. Whereas if you have an odd power, you get exactly that prime to the 1/2. So there's various ways to say this. I usually write this as square free part of a. It's just the product of all primes that appear in the factorization of a with an odd exponent, and it's that to the 1/2. So that's sort of, it's sort of some measure of how far a is from being a square. And if for an m, it would be sort of some measure of how far a was from being an mth power. Okay, so with this notation established, sorry, I'm just plugging in my computer. I realize it's unplugged. I want to make sure we have battery through the whole thing. With that notation established, let's choose 3 integers, which I'm going to call m0, m1, and m infinity for reasons that I'll say later, or the sort of P1 minus 3 points fans will already be able to intuit. But for now, they're just notations. Okay, ready? Now, I'm going to make a function. For any 2 coprime integers a, b, I'm going to write something that's going to look kind of nasty, and then we'll sort of do some examples of it and see that it's a somewhat reasonable quantity. Given these 2 integers, I'm going to define, let's see, is this readable? A to the sort of ceiling 1 over m0 minus m0, and then b to the same thing with m infinity, and then a minus b to the same thing with m1. And then finally, there's going to be this extra term, max of ab to the 1 over m0 plus 1 over m1 plus 1 over m infinity minus 1. So this is some crazy real number that I could compute attached to 2 integers a and b. And somehow you can, what you should take away from it is that it would be kind of small. Well, first of all, if a and b were small, that's going to make this thing small. But also if sort of a is close to being an m0 power, or if b is close to being an m infinity power, or if a minus b is close to being an m1 power, because that's what makes these kind of fake exponents small. So something about this is sort of should have a familiar feel, right? Somehow this would be very small if somehow you had, like, for instance, an mth power plus an m to the m1th power equaling an m infinity power. So a familiar kind of Diophantine question. But with this notion of size in mind, we can ask, how many pairs of integers are there where this measure is less than or equal to x? So, okay, let me give some silly examples and some not so silly examples. What if all these numbers are 1? Well, okay, so I should have said, if m is 1, then of course every number is an mth power, and so this is just always 1. So then these 3 terms disappear, and we're just doing the usual thing of counting pairs of integers. And in this case, let's see, 1 plus 1 plus 1 minus 1 is 2. So you're asking how many pairs of integers such that well, that their max is less than root x, so each one goes up to root x, so that's about x. I mean, constant times x. As I said, we're going to be very lazy about constant in this talk. I require it to be co-prime, so there's some constant there. Okay, here's another example. We could take m naught equals 3, and then the other two equals 1. Okay, so now then this thing is going to survive, and it's going to be a to the, oops, that should be a ceiling, not a floor, sorry. We'll make it in blue so you can see I messed it up. Times the max of a and b, and this is not so hard to work out. And if I worked it out correctly, it's on order of x log squared x. It's certainly an x to the 1 plus epsilon. I think it's a log squared. Another case, and this is one I sort of talked about as an example in a couple of talks I gave over the summer, is if all three of these numbers are 2. Now we have a question that, for the first time, really interleaves the multiplicative and additive structures, right? Because now we care about how close a is to being a square, how close b is to being a square, and how close a minus b is to being a square, as well as the overall size of the numbers. So our quantity is the square root of square free part of a times square free part of b. Oops, thought I had my highlighter on. Times square free part of a minus b times the max. How often can that be less than x? And this this was like a little beyond my ability to do analytic number theory, so I talked about it in a few talks. And indeed, this can be done. And so this is worked out independently by Pierre Le Boudec and by Bretton Nasserton and Stanley Xiao. I think this one is already on the archive, and this turns out to be on the order of, and maybe I'll even be a little more careful. I'll say it's between, our count is between an upper and lower constant times x log cubed x. So I want to distinguish, because here I didn't write down the constant, but one could work it out, I promise. Here, I think it actually, I think both of those folks working independently were like, okay, we can get the order of growth, but it seems hard to actually like pin down an asymptotic here for this question. So I think this is what we know. We know the order of growth is x times log cubed x, but not an asymptotic formula, like not what the constant is, or even more refinedly what the error term might be. And again, here's some questions and some brand new answers right off the shelf. But for a general m naught, m1, and m infinity, I don't know the answer to this question, although I have a guess that I'll tell you at the end. And it's probably the same guess like a sort of decent analytic number theorist would make, I would guess. That's a guess about a guess. Maybe I should say, by the way, that when I say general m naught, m1, and m infinity, it's worth mentioning, if you scroll back to this thing, if I choose like a really big m naught, m1, and m infinity, this is maybe not such a great question, because then this number, this exponent, is going to be negative. And once that happens, why should this count even be finite? Maybe there would be like choices of a and b where this became badly negative or something. So in fact, maybe I should say, we want to ask this question. So it's actually, I say general, but it's like a finite list of examples with 1 over m naught plus 1 over m1 plus 1 over m naught minus 1 greater than 0. And again, for those who have thought about a certain genre of Diophantine question, this condition is a very familiar one, and we'll come back to what it means in terms of stacks in a mo. Okay. One more question. And this is a question of, in some sense, there's like a big, long history of questions of this form, but I want to pick on this particular one for a reason. All right, how many points are there on P2? Okay, that sounds easy. But first of all, let's say they're algebraic points. So they're in P2 cube R. Okay, well, that's too many. So let's first of all say that I want the absolute Vaj height to be at most x. But now I want to say, actually, these are defined over a cubic field. So this is a question about cubic points on P2. And now, if you like, the Northcott principle, this is a finite set, and we can ask how it varies with X. And this was worked out by Quentin Guignard in 2017. So again, like pretty recent stuff, who shows that this is asymptotic. This grows on order X to the 12th, but there's a but. It turns out that this count is dominated by points which are on a cubic field, but which happen to lie on a Q rational line. And if you take out those points, you actually have a drastic decrease in the asymptotic. You get on order X to the 9 plus epsilon. So a much lower exponent if you throw out these points. But again, if you are used to, and of course, this is in the spirit of the so-called Batira-Rehmannian heuristics for counting rational points of bounded height and a variety. And we are very used to the notion of like accumulation. Like there's some special points you have to throw out, you know, this classic example being the points on a cubic surface that are on a line. But you know, there's only 27 lines, right? So you're not throwing out so much, you're throwing out a proper closed subvariety. And we know, thanks to work of Leroux-Dier and others, that sometimes you have to throw out a little bit more, like a thin set, in order to get the power of log right. But in order to get the exponent in Batira-Rehmannian right, you may have to throw out points in a proper closed subvariety, but these Q rational lines are all over P2, right? That's not you're not throwing out some closed locus. P2 is like a pretty homogeneous thing. It doesn't have like distinguished closed loci. Okay, so that's like a little bit, that's a very interesting result by Guignard, and I'm gonna come back to that in a minute too. And then of course, there are questions that if you've heard me talk before, you probably heard me say, so I'm not gonna, I usually would belabor them because they're very interesting, and I'm gonna belabor them a little bit less today. So, you know, I sort of entered this field many years ago thinking about the question of number field counting, thinking about how many Galois extensions of Q are there with some fixed Galois group G and discriminant, and then I'll say, or other ramification invariant, because there's different orders in which we can count number fields bounded by some constant X. And this is, of course, the circle of ideas known as Mala's conjecture and its many variants, which there has been like, you know, so much interesting work on in recent years. I think I saw Jia Wang in the audience. So Jia's work is only the most recent example of like the interesting progress towards this conjecture. And maybe I wrote this in small letters because I wasn't sure if I would have time to say it, but we're doing pretty well on time, so I think I'll comment on it. So for instance, of another variant that I think people have thought about less, I think if I zoom in, it zooms in for you guys too, right? Okay. So here we can read the small print. So what about if I count number fields, and in addition to bounding the discriminant, I also say, hey, I want there to be a short integer. I want there to be some alpha and OK. Ooh, and I'd better say not in Z. 1 doesn't count, or if there's like sort of some small subfield that doesn't count too. So I should really say an alpha generating OK. But I want it to be a short integer in the sense that all of its Archimedean values are bounded by some small power of the discriminant. And I wrote 0.01, but you could be much more loose than that. That is a question in the vein of what's called asking about the shape of a number field. Like, what is the nature of this integer lattice as a lattice? Like, what are its successive minima? So I'll say, you know, the work of Rob Heron, of Piper H, and several other people. So this is kind of a less studied, but I think in many ways equally interesting question that people are starting to think about. Okay, so those were questions. I could have even listed more, but let me kind of now say a little bit of what I see these questions as being. All of these are questions of the form, I take X in every case considered here a smooth proper Deligne-Mumford stack, and V some vector bundle on X. And then I'm asking how many points, how many rational points are there on this stack with height at most X? Phrased that way, it seems like a very natural question, right? It sort of sounds like, again, if we know about the Batira-Rehmannian conjectures, this is a question we ask about varieties all the time. I fix some height and I ask how many points are there of height at most X? And I'll just comment again, what I'm well, I am going to come to this, but like you guys have often seen me, or at least if you were at the trimester, you saw me give a series of talks about the question of what does this even mean? Because you won't look in the dictionary and find the definition of the height of a point on a stack over a global field. So I'll just say this is the work of myself, which is sort of still in preprint form, but I've sent it to many of you, and it'll be released soon, I promise. So actually, really everything in here sort of is the work of myself and Matt and David Zirk Brown, unless I say something that's incorrect because I didn't think about it enough, in which case that's just me and not them. So sometimes when I give,
I think we have a question from Colette Ellen in the chat. If you want to unmute yourself, which should now be possible.
Sure. Strangely, I'm not seeing. I have the chat open and I'm not seeing it. I wonder why. But I will take the question.
Yeah. Vector bundle V in this question.
What about the bundle?
Yeah, I mean, it's not. You have a question, and the vector bundle doesn't appear in the question.
Oh, yes, great. So part of the definition of height is that. So let's put this in. So note height here is with respect to a vector bundle, which is what we call V, on X, not necessarily a line bundle. So traditionally, our notion of height comes from placing a line bundle on a variety, and that's what gives us our height. We pull it back from the projective embedding. Well, that's if the line bundle is ample, right? So maybe very traditionally we say, okay, there's an ample line bundle. Then we kind of take the height machine philosophy and say, like, well, there's still a height even if it's not ample. You would express it as the difference of two amples, and maybe your height doesn't have good positivity properties or what have you. So in this context, it turns out, and depending on what we end up talking about, I may say more or less about this. It turns out to be not only possible, which is kind of an arid condition, but kind of necessary to say the things you want to say, to generalize and have height attached to a vector bundle and not just a line bundle. So in the examples I gave, the ones where that really matters are this one, the one with number fields. But we could make other examples where no, actually it matters for this one too. Okay. Okay, so let me now sort of go back to the questions I listed and sort of recast them from this point of view. So maybe the easiest one to see why this would be relevant is the one for counting 5 isogenies, because of course, if we are counting elliptic curves with a 5 isogeny, we're counting points on x naught of 5, and there's no way around it. Like x naught of 5 is a stack, like in a serious way, like because every elliptic curve has the plus or minus 1 automorphism that preserves that 5 isogeny, which means that x naught of 5 is a stack, which in stack language, like every point of it has generic inertia. So some of you guys like stacks and some of you guys don't. So let me put it to you this way. If I can say what makes this problem hard if you approach it from a very direct kind of analytic number theory style point of view. Like what makes this problem hard for like Heron and Snowden, for instance? Why don't they do it? Why do they do x1 of 5 and not x naught of 5? It's precisely because you have this problem. So let me write this in here. So the difficulty is that there are, if you think of it as like counting points on x1, you're like, oh, I know what that is. It's the J line. I just got to count J invariants. No, because there's lots of different elliptic curves with the same J invariant, right? So you think that's like a very naive fact that you learn in Silverman in the book, not the person who I saw was in the audience. And you think you're saying something like that you learned very early, but you're actually talking about stacks. So there are many elliptic curves with the same J invariant. And this is still true if you say and a 5 isogeny. Because if my elliptic curve has a 5 isogeny, its quadratic twists, which are the elliptic curves with the same J invariant, also have a 5 isogeny. And this turns out to make the counting problem substantially more difficult. But it doesn't happen. If I said a 5 torsion point, if my elliptic curve is a rational 5 torsion point, its quadratic twists do not. That picks out exactly one elliptic curve in this quadratic twist family. And that, from a sort of direct writing down equations point of view, it's sort of very plain, or I don't know if it's plain, but when you sit down and try to do it, you quickly find that that makes the problem much simpler, and that's what enables Heron and Snowden to do their thing. And from a sort of somewhat pretentious algebraic geometry point of view, what's reflected in that fact is the fact that x1 of 5, the moduli of elliptic curves with a 5 torsion point, is a fine moduli space. It's a scheme. It represents the functor you want, and so there's literally the points of that curve literally correspond to the things you're trying to count. For x0 of 5, if you sort of think of it naively as a curve with an equation, which in algebraic geometry you would say is like looking at the coarse moduli space, the points of x0 of 5 in that naive sense do not correspond to the things you're trying to count. You have multiple quadratic twists in the same elliptic curve that correspond to the same point in x0 of 5. So what we would say in a more modern language is that we really should be thinking of the x0 of 5 as an algebraic stack whose points are like a richer thing than just the points on the sort of naive curve that you sort of write an equation for. And counting points on that stack is really the question that you're asked to solve, but that's inherently more complicated. That being said, we can do it, or I can't do it. Soumya and Brandon can do it. So your stack is x0 of 5. In this case, the line bundle with the vector bundle, with respect to which you would account, is a line bundle, and in fact, it's the Hodge bundle, which comes naturally from what it parameterizes, the bundle whose sections are weight 1 modular forms. And in the end, then you're like, oh my gosh, I'm going to learn this exciting new definition of height, but not really, because it turns out that with this definition, if you sort of like scrumble through what our definition gives, it gives us the height of an elliptic curve with minimal Weierstrass y squared equals x cubed plus ax plus b is indeed just what you might think. It's max of a cubed b squared. Well, it's not to the 1/12 actually. So what we thought was the naive height, maybe we're sort of trying to like rehabilitate it and say it's not so naive. It is like in fact like what you get using a natural notion of height on a stack. Okay, so that's that example. What about this kind of crazy function, capital H sub m0 m1 in infinity? Well, that corresponds to the following stack. I think one of the favorites of people who ever started studying this, which we draw a picture of like this. I take P1, but then I'm going to do something mean to it. I'm going to cut out the points 0, 1, and infinity, as one does, and I'm going to replace them with a 1 over m0 of a point, a 1 over m1 of a point, and a 1 over m infinity of a point. Okay, what does that mean? Oh, Stanley's here. Hi, Stanley. Okay, so Stanley Xiao, whose result I just quoted, is in the audience. I see him in the chat. What does this actually mean? I don't necessarily want to say too much, but let me say for those who like stacks, I'll just comment that what you're really doing here is cutting out a point and replacing it with the classifying stack of the group scheme of M infinity with unity, and the same for the others. But it's one of those things where let's talk about what its properties are and don't worry so much about like why such a stack exists. So first of all, I will comment, I think for most of us of a certain age, where did we first learn about this stack? We learned about it not in the language of stacks at all. This is what comes up. I said that this has to do with like this, somehow our points in this problem, this measure of size we use, seems to have to do with like, how can you have an mth power plus an m plus first power, sorry, an mth power, m naught power plus an m1 power equals an m infinity power. It's kind of like what we'd call a generalized Fermat equation, right? Almost the very first kind of problem in diaphantine geometry I ever worked on when I was a new postdoc. You know, a to the p plus b to the q equals c to the r. And going back to the 90s, I don't know if you remember this, but there was like a banker who said he would give like $1 million to anybody who could classify all solutions to this generalized Fermat equation. But his only condition was that it be named, the conjecture be named after him and not called generalized Fermat anymore. And there was like a big fight. He got in a big fight with a lot of people because he was like, I won't give the money unless it's like named after me. It's like I paid for it, so it should be like my, it should be my conjecture. And if somebody proves it and I pay them, it should be like my theorem. And there was like a big fight. Well, anyway, it was like never proved, and he kept his money. And then he became one of Donald Trump's biggest donors in Texas. And that's where the money went, to see if somebody had proved this, then he wouldn't have that money. I'm just saying. Okay. But one of the guys who fought with him about this was our friend Andrew Granville. And I'll just comment that if you want to sort of see a very down-to-earth view on this stack, look at the wonderful paper of Darmon and Granville from the 90s, where they prove at least that a generalized Fermat equation like this has finitely many solutions. And they kind of don't really say that. I don't even think they say the word stack in the paper, but if you look at what they do, and of course, I think they knew this, but Andrew would never say stack, right? He would steadfastly avoid it. They're essentially making an argument that this stack is étal covered by a high genus curve and applying faulting. So I'll just comment that it's a wonderful paper that people should look at. Okay, coming back to the main point, this kind of crazy function that I wrote down is in fact what we would call the anti-canonical height on this curve. So the theory of the theory of stacks like this is pretty well understood. My collaborator David Zurich Brown has written a ton about it. He has a wonderful paper with John Voigt that like makes everything very explicit. So maybe I'll also recommend that awesome paper. Stacky curves. I mean, this particular kind of curve, because it's birational to P1, is easier than others. And I should say again, for those who are used to material binding philosophy, the sort of basic rule is supposed to be that if you count points by anti-canonical height, there's supposed to be about X of them. That's like your bedrock case that you start from. Or maybe, X to the 1 plus epsilon, maybe there's some logs, something like that. And so that is in fact what we would predict here, that if you count points on a stacky curve like this by anti-canonical height, you get the count should be on order X to the 1 plus epsilon. That being said, a couple comments, and I guess, yeah, here I'll like literally say it. So first of all, of course, another core thing of material binding philosophy is that you're only supposed to do it in situations where the anti-canonical is ample, right? Otherwise, you're not going to get points. So the analog of that here is this condition of positivity that 1 over m naught plus 1 over m1 plus 1 over m infinity minus 1 is bigger than 0. That's in fact the Euler characteristic of this curve. Or maybe it's the negative Euler characteristic. And we would conjecture that under those conditions, the number of points with that height bounded is between x and 1 and x to the 1 plus epsilon. And indeed, it seems quite reasonable to say, okay, it's probably asymptotic to some constant times x times some power of log. But I will be honest and say I am actually not sure what the power of log should be. And actually, I did not know for this question about the square free parts that that Stanley and Brett and Pierre solved. I did not know it was going to be log cubed, actually. So I just want to be honest. I mean, I was pretty sure it was going to be on order of x to the 1 plus epsilon, but they seem to have showed that the right order of growth is log cubed, and I don't quite know what to expect for a general. And maybe Stanley knows what it's supposed to be. I don't know. Stanley, did you know it was going to be log cubed before you worked it out, or do you have to work it out and then? Okay, because I don't really have a mental heuristic for that yet.
I thought it was going to be log squared.
I'm going to be honest with you. I think I also thought it was going to be log squared. But I didn't want to say I thought the wrong thing. I just wanted to say I didn't know. But the truth is I kind of thought it was going to be log squared. Okay. But no, I didn't have a good reason. Okay. I did some computations that made me think that. Okay. So yeah, maybe I'll comment in a slightly different direction, but I do think this is kind of a cool connection, so I want to mention it. So again, this stack Ex is birational to P1. So by the way, one thing I like about this subject is like, for somebody like me who likes curves and was always a little intimidated by birational geometry because you have to understand higher dimensional varieties, which is very hard. So now you can do birational geometry, but on curves, because you can have a smooth projective one-dimensional stack, which is birational to P1, but it's definitely not P1. That's kind of cool. But in particular, what this means is that because it's birational to P1, the rational points of Eeks and the rational points of P1 are basically the same. Okay, there's some sort of extra ones which are like supported on these three special points. But apart from those, apart from the, like that closed subvariety, substack, I should say, the rational points are identical. All that's different is that we're counting them in a different order. Our height function is very different from the sort of standard height function on P1. So I mean, one part of this philosophy is like, and in a way, this would be the same with like, rational surfaces. They're all birational to P2, but so you could say, oh, same points, basically. Yeah, but you're counting them in a very different order. And so as you guys know, who have worked on material modeling, like the counting problems are completely different for different rational surfaces. Same deal. So I'll comment that, as I said, you can compute the Euler characteristic of this stack if you declare that what genus means is that 2 minus 2g is equal to, oh, I forgot to erase my scratch work. How embarrassing. Okay, let's not look at that. The 2 minus 2g is Euler characteristic. Then you get this formula that the so-called genus of this stack is this quantity in terms of the m naught, m1, and m infinity. So one way of saying this question I asked that Stanley worked on and solved is it's about counting points of bounded height on a curve of genus 3/4. And there's a lovely theorem by Bhargava and Poonen, also from this year, that a stocky curve in this sense of genus less than a half has a local to global principle for integral points. So it's you're closer to genus 0, right? So you sort of have more rational points. And actually, in fact, I think this was a student of Bjorn's, Atticus Christensen, also proved this year that you even get strong approximation. On the other hand, in genus between bigger than 1/2, maybe not. And they give an example of a curve of genus, a stocky curve of genus exactly 1/2, which does not have a Hasse principle for integral points. So it has integral points everywhere locally, but no integral points globally. So somehow there's some interesting story of these stacky curves intermediate between 0 and 1, both in terms of questions like strong approximation, which are not about counting, which are not about heights, but also I think for these questions about counting by height. And my intuition would be that probably as the genus kind of gets closer to 1, like as the Euler characteristic gets closer to 0, the problems probably get harder. So I guess my guess would be that the sort of 1/2, 1/3, 1/5 case, that's always the hardest. And my guess is that that would be the hardest case here too. So counting those points, the kind of icosahedral case, if you like, my guess would be that would be the hardest. By the way, having said one piece of philosophy, I now want to counteract it because, we're, again, for people who study Battir modeling, we're very used to the idea that if you count points of anti-canonical height at most x, that should be on order x or x times log x to some power or something like that. But definitely not always. And indeed, the case that I probably started out thinking about is the case that's relevant to counting G extensions. That turns out to be the case where the stack is just the classifying stack of a finite group. So that's, I mean, it's hard to draw a picture of, right? It's just like literally like a point modulo G, which if you're not stackitized already is maybe not such a meaningful concept, but it is an algebraic stack of 0-dimensional. And what you need to know about it is that it's anti-canonical. It has a perfectly good anti-canonical line bundle, but it's 0. So if you count with respect to that, you get utter trash. So I will say that the conjecture is not going to be count by anti-canonical height and the power of x is 1. It's more complicated than that. Okay, one more comment, because there was one of the problems I listed that I didn't get to talk about, and then we'll sort of finish off at about 50 or 55. For cubic points on P2, the stack we want to consider is just sort of the symmetric cube of P2. So P2 cubed modulo S3, but now I mean this in a kind of stacky sense. And if you look at what our conjecture says about how many points there are supposed to be of bounded absolute Vé height, which you have to compare to the heights that we study, you get this x to the 9th. Remember, that's what Guignard found. That's how many points there were away from these weird ones that lay on a Q rational line. And what I want to point out is that if you look at those points on P2, it looks like there's Zariski dense all over the place. But if you think of a cubic point on P2 as a rational point on Eeks, they actually lie on a closed subvariety. And so you could have come back to this notion that you're throwing out a closed locus, and once you do that, you can get the power of X right. And I should point out actually that really this insight is due to, okay, I hope I'm spelling her name right, Le Rudelier, Cecilia Le Rudelier, who she wasn't using stacks, but she observed that you should think of the accumulation as a property that takes place on the symmetric power of the variety, where what might look Zariski dense is actually a closed locus in that. Okay, so to finish off, here's the question that's certainly in my mind, and maybe it's in yours too. I keep on saying we have this conjecture. Why am I not stating it? Why am I not just writing down, like, here's the conjecture? Okay, first of all, we write it down in the preprint. It's a little complicated, and there's something unsatisfactory on it that I want to present as a kind of challenge to the room. And I'm going to say what is, to my mind, unsatisfactory about the form that the conjecture presently takes. Okay, so again, oh, Le Rudelier, thank you. Sorry. So a key element of this material mining conjecture is that you take some line bundle and you want to know, maybe it's effective. You want to sort of move the canonical divisor by some multiple of your line bundle to make it effective. And so it's the so-called Fujita invariant. But what it really depends on, if you've not thought about this before, this is not going to be so meaningful. All I want you to take away from it is that it relies on this notion of the effective cone. In the world of line bundles on a variety, you have this geometric notion of effectivity, and you have to know what that means. So this is what we lack. This is what we lack in the present context. If I give you a vector bundle on a stack, I don't know what it means or should mean to say that it's effective. I don't even really know what it means to say that it's ample, although there's some people who have proposed definitions of that which don't quite seem to match what we want. So I mean, there's a geometric criterion that's lacking, and I'll tell you what we do as kind of a hack, okay? So let's imagine, if you will, that we were trying to set up conjectures a la Batira-Admani. We were trying to count rational points, but somehow we had never developed the notion of an effective line bundle or an ample line bundle. All you knew how to do was be a number theorist and look at points over global fields, okay? What an impoverished world it would be. Okay, but if you were in that world, what would you do? You'd be like, well, what I think an effective line bundle means is I look at rational points and I look at their heights with respect to that line bundle. Hey, and I notice that they're always positive. And then you're like, well, maybe it's effective. Maybe there's some exceptional divisors. Okay, so on some exceptional divisor, maybe it's negative, but like on an open locus, the height I associate to this line bundle is always non-negative. And maybe that's what I, at least away from a locus. And maybe that's what I mean by effective. Now that would be sort of a ridiculous thing to mean by effective, because we know it has a geometric meaning, right? It somehow seems irrelevant to bring in rational points into that question. But in this context, that's basically all we've got. So this is not a sort of precise statement, but roughly speaking, our notion of what it means for a vector bundle to be like suitably effective or ample or positive or whatever is that, at least away from some closed locus, you have a kind of Northcott property for that bundle that if you look at, and why do you have to do this thing about algebraic points of degree less than or equal to d? Because maybe you don't have rational points for some reason. Maybe you want to sort of extend to some field. As I said, it's a little bit hacky. It gives an answer, but there should be a geometric way to say this that we do not know. It's one of those things where it feels a little circular. It's not literally circular in the logical sense, but it's conceptually kind of circular. We're making a conjecture about points over Q or points over some fixed global field by means of some criteria that has to do with knowing something about points over the algebraic closure, and it shouldn't be that way. So all that being said, there is a conjecture written down. When you plug it into the various stacks we've talked about, it kind of returns the usual Batira-Admani when you apply it to a scheme. It gives the usual Mala conjecture when you apply it to the classifying stack of BG. It gives the examples that we've talked about in this talk. It sort of correctly predicts things, which in a few cases we now know are true. I will comment. I do because I saw he's here. I just do want to point out that in the guts of our definition of height, it definitely owes a lot to the work of Yasuda, who is here, and also I think it was from Yasuda that he really pushed forward the philosophy that these questions of the Mala type and questions of Batira-Manin type should be unified somehow. That those should be, and that's certainly the philosophy that we have too. And maybe I'll just close by saying things that I did not discuss in this talk. So I definitely successfully talked about stuff I don't usually have time to talk about, and yet, of course, even here, now maybe next time I'll talk about the stuff that I didn't have time to do in this talk. I didn't talk about the relationship with the work of Dan Abramovich and Tony Verrilli Alvarado. I think Dan is here, so sorry for that, but who kind of, and actually what they do, all right, hold the thought of Dan, because I'm gonna say something about Vojta at the end. I didn't talk about the relationship between the wonderful work of Emmanuel Perre and freeness of rational points, and all that's followed from that. That is highly relevant to the question of counting with respect to a vector bundle instead of a line bundle, which is relevant even for schemes. And in fact, that's kind of related to what Perre is doing. And so in some sense, if you skip back to these questions about these questions about shapes of number fields, like where is it? Like counting number fields with a short integer. I think this world, which is mostly being done by kind of Bhargava style algebraic number theory, arithmetic statistics people, should be thought of as the kind of stacky analog of Emmanuel's question about like free rational points on varieties. So I think that's like a very interesting open area to kind of interpolate between this work on freeness and this work on this kind of coming out of the Bhargava school of arithmetic statistics. All right, wait, last thing. Oh, right. And this is kind of also where it ties in with it, and this is discussed quite a bit in Dan and Tony's work. We've talked a lot about varieties with a lot of points, where the anti-canonical is in whatever this is supposed to mean, positive. But you can also ask about what happens in a situation where there's supposed to be few points. So that's less in the realm of Batira-Manin and more in the realm of Vojta's conjecture. So I'll just give like a couple of examples of sort of stacky Vojta type questions, which are also related to Dan and Tony. So here's a question off the top of my head that I wrote down, and I thought I would find some like British guy from 1930 who proved this, because it seems like that kind of thing, but I couldn't find one. So maybe you can, or maybe somebody can prove this. Are there only finitely many 5-term arithmetic progressions so that if I times them all together and take the square free part, so first of all, you guys probably know you can't have 5 squares in arithmetic progression. Does everybody know this? I don't know, but I promise you could prove that. That's a classical fact. I think you can't even have 4 actually, but that's sort of close to the boundary. You definitely can't have 5. So this would be sort of a quantitative version of that for any positive delta, if you take this, like not only can 5 terms in arithmetic progression not all be squares, but you can't even get that close. If you take their product and take the square free part, that's at least as big as the maximum term of the arithmetic progression to the 0.49999. That seems to be like that would be like a natural analog of Vojta's conjecture applied to like a P1 with 5 half points on it. So this is the relevant stack. And I think, I haven't really checked, but Paul wrote down what he called a more general ABC conjecture. So I think in the 90s, that's the problem with the ABC conjecture, right? It's not general enough. Okay, but there is a more general ABC conjecture due to Vojta. That, of course, is far beyond any capacity we have to prove stuff. But I think this kind of stacky Vojta gives you examples that maybe are more tractable, like a sort of first steps towards that. So, and so maybe this sort of as with the question that Pierre and Stanley and Brett answered, which I didn't know how to do, but it wasn't like utterly shocking that it was within the realm of people who actually had technique. For all I know, maybe somebody in the room can actually prove this, because I'm not enough of an analytic number theorist to sort of know whether this is. I can see it's not trivial, but I don't know that it's whether it's doable. And finally, I'll just say, another example coming from if you were to sort of take an abelian variety on mod out by plus or minus 1, which is a stack. It has sort of stackiness at the 2 torsion points. There's a kind of interesting prediction. I'll just sort of mention it because I didn't work it out fully enough to really want to talk about it too much. That seems to suggest that if you look at quadratic twists of an abelian variety of dimension at least 3, now we know by kind of functional equation considerations that a lot of those quadratic twists are going to have positive rank, or at least that's what we expect. But the prediction would be that it's very rare, apart from maybe some closed locus, for the points in those quadratic twists to be low height. You would expect those points to be of height that's rather large relative to the twist. Actually, I've never asked Joe about this, but I think he's in the audience. But I think it seems like the sort of thing that next time Joe Silverman and I are having coffee, I'll like ask him if he thinks anything like this is reasonable. Okay, so we are at 56. Great time to stop. I'm happy to take any questions either now or in GatherTown after. I'll answer Timo's question. Can you? Yes, absolutely. So it gives you the same constants that. Well, okay. Our conjecture as we've written it, we are not bold enough to conjecture the power of log. There's some cases where you can guess it, but it's complicated. So I would say it gets the same A that Mala gets. It gets the same power of X that Mala gets. And well, by constants, Timo, do you mean the exponents or like the literal constant that you multiply X times log X to something by?
So actually, perhaps Jordan could just explain for the people who can't easily see the chat what the question was.
Oh yeah, okay. So let me say what Mala predicts is that the number of G extensions of discriminant at most X of some global field K is asymptotic to, let's see if I get all the dependencies right, some constant that depends on everything, times some power of X, which depends only on the group, times some power of log X, which depends again on the group and the field. And our conjecture applied to BG, yeah, it predicts the same value of A that Mala predicts. Getting the B right is much more subtle, and indeed Mala's original thing had to be modified a bit. And I actually just learned from Gia, who I think is here. So I had a student, Seifi Turkelli, who wrote a beautiful paper fixing the power of log in Mala's conjecture, or so I thought, but Gia says that Seifi's thing is also wrong, or like needs yet further refinement. So I haven't read that paper yet, but in any event, even the power of this B is very subtle. Like a lot of ink has been spilled on sort of trying to get it right, even in this case of G extensions. So I think it's there's something subtle about it. So to Takahiko's question, do we use the regular representation as a vector bundle on BG? So what's great is you can use any vector bundle you like. So I would say the typical thing, so which vector bundle? So first of all, again, for the people who are not fully stacketized, this sounds like I'm sort of saying something like incredibly highbrow thing, but guess what? A vector bundle on BG just means a representation of G. That's just how pretentious people say a representation of G. So i.e., which representation of G, and you have choices, okay, right? So let's say, and each choice of vector bundle gives you a different height, just like in classical Bayes theory, each line bundle gives you a different height. So ready? I will tell you what they are, because this is very relevant since Takahiko asked. So regular rep of G gives discriminant of the Galois G extension, whereas the permutation rep of Sn, which is really different from the regular representation, right? Much smaller. It gives you the discriminant of the degree n extension with Galois closure having the Galois group Sn. So this is sort of both a triviality and deep at the same time. Like if I take a degree n extension whose Galois closure has Galois group Sn, there's two different invariants I can assign to it. I could take the discriminant of the degree n extension, which is what a normal person does, or I could take the Galois closure and take the discriminant of that. And those two things are not the same. They're not even related in some particularly nice way. They're just two different invariants. And if you count number fields with respect to those two invariants, you're counting in a different order. Actually, this is all the way back. I mean, this is something Akshay and I thought about a long time ago. And I think Melanie Wood was the first person to really push through an example where counting cubic extensions by discriminant was well understood. And Melanie thought about the problem of counting the Galois sextics, like counting the Galois closures by their discriminant. I think that was when she was a grad student. She was thinking about that. And I'll just comment that you may say, is this just kind of generalization for generalization's sake? But for instance, okay, I hope what I'm going to say is strictly right. And if any of the authors are in the chat, they can tell me. But for instance, D4, wonderful example. Traditionally, you think of that as a kind of quartic extension. So you think of its permutation representation, right? D4 acting on 4 things. I think Henri Cohen and Diaz and Olivier were the first people to count those. But it also has a 2-dimensional representation, which is also like pretty natural. And if you count with respect to that, that is the new count of D4 extensions by, oh my gosh, okay. Can anybody yell out the authors of this paper? I always think of it as Ila's paper because I know her. I think Varma Shankar, right?
Ila Varma, Arul Shankar, and Kevin H. Wilson.
Awesome, thank you. Right, so they count the D4 extensions in a different way, and that's somehow the right way in the sense that you get a nice Euler product, and it's clearly somehow like the right counting to do. And one interpretation is that they're counting with respect, instead of counting with respect to the 4-dimensional permutation representation, they're counting with respect to this more natural sort of 2-dimensional representation given by the symmetries of the square. So again, I think that there's a lot of philosophy, but we don't always really know. You know, different vector bundles give different kinds of counts. And maybe some of them end up having better properties in terms of like what, you know, best possible is like the count ends up being constant times power of x times power of log, where the constant is an Euler product. And if you count with respect to local conditions, you're just dropping factors off that Euler product. That's somehow the best case scenario. And we know that that's sometimes the case and sometimes not.
Well, thank you, Jordan, for this talk. Let's unmute ourselves.